Assalamu alaikum. My name is Usfahan. I am from Department of BS Physics holding ID 007. Today I am going to give a presentation for my subject of Principles of Chemistry 2 and my resource person is Dr. Hammad Majeed. So the topic that is assigned to me for a presentation is NMR spectroscopy. So first of all, what is spectroscopy? Spectroscopy is the study of the absorption and emission of light and other radiations by matter. Now, NMR stands for nuclear magnetic resonance. It is spectroscopy technique based on the absorption of electromagnetic radiation in the radio frequency region of 4 to 900 megahertz by the nuclei of atoms. This analytical technique is used to characterize organic molecules by identifying carbon-hydrogen frameworks within molecules. It is the most powerful tool available for organic structure determinations, and it is a research technique that exploits the magnetic properties of the certain nuclei. So here is the principle of NMR. Protons in different environments absorbs at slightly different frequencies, so they are distinguishable by NMR. And the frequency at which a particular proton absorbs is determined by its electronic environment. The size of the magnetic field generated by the electron around a proton determines where it absorbs. Now, what is nuclear spin? A nucleus with an odd atomic number or the odd mass number has a nuclear spin, and the spinning charged nucleus generates a magnetic field. As we all know, a moving charge has a magnetic field created by itself around itself, and all the charges that are at rest have electric field. So that charge is moving, that is our proton, that has magnetic field around itself, and when we apply an external magnetic field, there is difference between its magnetic field that will give rise to the NMR spectrum. So here you can see the spinning protons, then the loop of current generated around that proton, and these field lines generated from north pole and ends to the south pole and forms a bar magnet. Now, external magnetic field. An external magnetic field B naught applies a force to a small bar magnet, twisting the bar magnet to align it with the external field. And the arrangement of the bar magnet aligned with the field is lower in energy than the arrangement aligned against the field. Here you can see there is external magnetic field in which a bar magnet, that is our proton, it will twist itself and align itself against the magnetic field. That is, if external magnetic field's upside a magnet has a south pole on upside, then our bar magnet will turn itself, twist itself, and forms north pole on its upper side. Then every spectroscopy technique requires some source of energy for spectroscopy to happen. So the source for NMR is the source of energy in NMR is radio waves, which has long wavelength having more than 107 nanometers, and thus low energy and frequency, as wavelength and energy and frequency are inversely proportional to each other. So if wavelength is long for radio waves, then their energy and frequency is way too low than other waves. When low energy radio waves interact with molecules, they can change the nuclear spin of some elements, including 1 hydrogen and 13 carbon. Here is electromagnetic spectrum. Here you can see radio waves have the longest wavelength than other waves. Then this is the theory for NMR. In a magnetic field, there are now two energy states for a proton, a lower energy state with the nucleus aligned in the same direction as B naught, and a higher energy state in which the nucleus aligned against B naught. When it was in lower energy state, it will align itself in the same direction to the B naught, as it has no not much energy to align itself against the uh, external magnet. So it will in same direction with that external magnetic field. So when an external energy source that matches the energy difference between these two states is applied, energy is absorbed, causing the nucleus to spin flip from one orientation to another. And the energy difference between these two nuclear spin states correspond to the low frequency radio frequency region of the electromagnetic spectrum. Now, effect of magnetic field. As you can see, a spinning proton creates a magnetic field around itself. And when there is no external magnetic field is applied, the protons are randomly oriented in direction. And when the external magnetic field is applied, they will align themselves with or against the magnetic field, that is B naught. Two variables characterize NMR. The first one is applied magnetic field, the strength of which is measured in Tesla. This is the unit for the strength of magnetic field. And the second one is frequency of radiations used for resonance, measured in hertz or megahertz. We mostly use megahertz. And a nucleus is in resonance when it absorbs radio frequency radiations and spin flips to the higher energy state. As when there is no absorption of radio frequency radiations, it is in its lower state. But when it absorbs the radio frequency, it will it will get excited and goes into its high energy state. And a nucleus is in resonance when it absorbs RF radiation and spin flips to the higher energy states. In this diagram, you can see proton is in lower energy state, then it absorbs energy and causes the nucleus to flip its spin. And when it goes into high energy state, it will stay for some time here. And when it comes back to its lower energy state, again, it will change its orientation because of losing the energy that it has absorbed before. Now, instrumentation for NMR, it contains sample tube, that is also known as sample holder, then a permanent magnet that has two poles, north and south pole, then have a sweep generator, then magnetic coil that is wrapped around that sample tube or sample holder, then sweep generator that generates that helps these permanent magnets to generate a strong magnetic field, then radio frequency transmitter that will give the radio frequency to that sample solution, and radio frequency receiver that will receive that radio frequency when it uh, comes back to its lower energy state and emits radiation, then readout system that is normally oscilloscope, which gives rise to NMR spectrum. Now, the most important is how it works. The sample is dissolved in a solvent, usually CdCl3, that is deuteriochloroform, and placed in a magnetic field. A radio frequency generator that then irradiates the sample with a short pulse of radiation, causing resonance. And when the nuclei fall back to the lower energy state, the detector measures the energy released and the spectrum is recorded. In this diagram, you can see there is two magnet, that is two poles, a north and a south pole, and that forms a high magnetic field. And this will give the orientation according to which they will change. The protons will change their orientation, whether they are oriented with the external magnetic field or against the magnetic field. Now, alpha spin and beta spin state. In NMR, there are two spin states. The lower energy state with a proton aligned with the field is called alpha spin state. When it hasn't absorbed any energy, it is in alpha spin state. And the higher energy state with the proton aligned against the external magnetic field is called the beta spin state. And it happens when we give some radio frequency to the sample, and the proton will excite and go into its higher energy state, and that will give rise to beta spin state. Then again, when it will de-excite, it will emit radiations, and these radiations were recorded by radio frequency receiver, and after that it will give two readout system that will form the spectrum. A nucleus is in resonance when it is irradiated with radio frequency photons having equal energy to the energy difference between the spin states. And under these conditions, a proton in the alpha spin state can absorb a photon and flip to the beta spin state. Here you can see alpha spin state. When a proton is in alpha spin state, it will absorb the energy, that is radio frequency photon, and uh, reaches the beta spin state. And when beta spin state releases energy, that will give signal detected by NMR. It will give rise to beta spin state. Now there is an effect, that is chemical shielding effect in NMR. The relative energy of resonance of a particular nucleus resulting from its local environment is called the chemical shift. NMR spectra show applied field strength increasing from left to right. Here you can see that is left to right. Then left part is downfield, the right part is upfield. Nuclei that absorb on upfield side are strongly shielded, where the nuclei that absorb a downfield side is weakly shielded. Here you can see the electrons surrounding a nucleus affect the effective magnetic field sensed by the nucleus, that is external magnetic field. So on that downfield left side, there are deshielded nuclei, and these protons senses a larger effective magnetic field, so come into resonance at higher frequency. And on the upfield, there are shielded nuclei, and these protons senses a smaller effective magnetic field, so come into resonance at a lower frequency. Now, factors affecting the chemical shift. Electronegative group or inductive effect. Now, electronegative group attached to carbon-hydrogen system decreases the electron density around the protons, and there is less shielding and chemical shift increases. Now, the magnetic anisotropy of pi system. Magnetic anisotropy means there is a non-uniform magnetic field, and electrons in pi system like alkenes, aromatics, alkynes interact with the applied field, which induces a magnetic field that causes the anisotropy, and it causes both shielding and deshielding of protons. Then here comes hydrogen bonding. Now, protons that are involved in hydrogen bonding are typically change the chemical shift values. The more hydrogen bonding, the more proton is deshielded and chemical shift value is higher. Now, van der Waals deshielding. The electron cloud of a bulkier group will tend to repel the electron cloud surrounding the proton, such as a proton will be deshielded and will resonate at slightly higher value of delta than expected in the absence of this effect. Then effect of temperature, and this says resonance positions of most signals is little affected by temperature. Effect of solvent. Chemical shift changes when the solvent changes from chloroform to CtCl3, but change to more polar solvents like methanol. The solvents used in NMR are CCl4, CS2, CdCl3, C6D6, C2 or D2O. Then proton NMR. This is a type of NMR, as there are two types of NMR, that is C13 NMR and then proton NMR. I will discuss about proton NMR. The most common form of NMR is based on the hydrogen one, nucleus or proton. It can give information about the structure of any molecule containing hydrogen atoms. And here comes the interpretation of 1H NMR spectra. Now, the things we get on NMR spectra is number of signals, then position of signals, relative intensity of proton, then splitting of signals. So number of signals indicates how many different kind of protons are present As you can see in the spectra, there are two types of carbon hydrogen framework, that is CH3 and CH2. These both have different peak and there are how many different types of carbon hydrogen interactions or protons present. Now, position of signals. It indicates something about chemical shift, magnetic environment of proton. Then relative intensity of proton, proportional to the number of protons present. Now, splitting of signals indicates the number of nearby nucleus, that is, spin-spin coupling, usually protons. Now, acquisition of spectra. The received nuclear magnetic resonance response is very weak in signal and requires a sensitive radio receiver to pick up. A Fourier transform is done to extract the frequency domain spectrum from the raw time domain spectrum. Good hydrogen NMR spectra can be acquired with 16 beats, which takes only minutes. However, for heavier elements than hydrogen, acquisition of quantitative heavy element spectra can be time consuming, taking 10 of minutes to hours. Then, an average of all the acquired spectra will be generated and displayed through the graph. Here is the NMR spectra for ethanol. Here you can see the peak for CH3 methyl group is higher one, then CH2, and the last one is OH where one hydrogen present. Now, applications of NMR. Proton NMR used for structural elucidation of organic and inorganic solids. It determines the physical and chemical properties of atoms. There are various applications in medicine of NMR like MRI, then anatomical imaging. This also involves the imaging of brain, abdomen, etc. Then measuring psychological function. It also distinguishes between white matter and gray matter of our brain. That is now the flow measurement and angiography. Then tissue perfusion studies, then tumors and MRI. And these are the references from which I collected all the material. And that's all from my side. Thank you so much for your attention.